Hello, let us go through the solutions of homework 2. First question of homework 2 had to do with the difference between FT and fmax, which one depends on layout, and an additional question was if we are operating close or even beyond the FT, assuming that the fmax is higher than FT, fmax can be higher or lower than FT, what does this imply for the matching networks? First of all, as we have seen in the course, fmax is a frequency where if you do complex conjugate matching and if you can do the complex conjugate matching in a lossless way, then fmax tells you the frequency where the power gain after doing complex conjugate matching becomes equal to 1. Ft is then the point where the current gain becomes equal to 1. In order to get the highest current, you need to drive the transistor with the current source and you need to short circuit the transistor in AC for high frequencies in order to measure the maximum current you can get from a transistor. And fmax depends on the layout because it heavily depends on your resistors and especially the gate resistance, but also the drain and source resistance, but especially the gate resistance is something that we can minimize by drawing the transistor in a clever way. And that also means why FT is interesting, because FT does not depend on the layout. It is more something about the junctions and the oxides, so it is much more fundamental. Now, if you operate beyond the FT, assuming fmax is higher than FT, then this has an important consequence on the matching networks, because we have seen that fmax can be written as it's proportional to FT, but also proportional to the square root of the output resistance, which is typically a small signal output resistance, divided by the gate resistance, which is typically a physical resistance of the gate electrode. So if fmax is much higher than FT in your technology, this often happens in CMOS, doesn't very often in bipolars, but in CMOS fmax can be higher than FT. It means that actually this ratio is very large. It means that we have a transistor with a very large output resistance and a very small gate resistance. That also means that if you're operating beyond the FT, that means the current gain is smaller than 1, and that automatically means that the voltage gain has to be very large. Now all this implies that you're going to have more difficulties with the matching networks if fmax and FT are far away from each other, because in the end you would like to match the high output resistance to, for example, 50 ohm, and at the same time you want to match the very small gate resistance also to 50 ohm. And the further those two numbers get away from each other, the more difficult it will be in general to realize these matching networks. So that's the reason why fmax can be higher than FT, but having an fmax which is much higher than FT, it does come with some challenges towards the matching networks. Second question in homework 2 had to do with transistor layouts. And let me just very briefly go back to the actual question. Here we are. We had a transistor on the left, transistor A. We had a transistor on the right, transistor B. And the question is, what is the difference? And if you look at the layout, the big difference is in the gate connection over here. On the left side, you see that we simply have a few fingers here, and that's it. This is not double-sided contacted. This distance is fairly large for the transistor on the left. It is much smaller for the transistor on the right. And for the transistor on the right, we also contact the gate fingers or the gate electrodes on both sides. So those are two arguments why transistor B will have way lower gate resistance, and as a consequence it will have a much higher fmax. So that's the conclusion or the solution, you can say, for question 2b. Transistor B will have a much higher fmax. But there might be actually a good reason to still use transistor A. First of all, if you do the simulation in CUX and you've set everything up correctly, then you will see this is the fmax for transistor A below 100 gigahertz. This is the fmax of transistor B close to 200 gigahertz. But what we also see is that the input and to some extent also the output resistance, they are actually closer to 50 ohm for transistor A. So it will be easier to do a complex conjugate matching of transistor A, and you will have less losses in your matching networks. Also, the bandwidth will be easier to achieve with transistor A because the Q factor of the RC network at the input, also at the output, is lower in transistor A. So easier to match and higher bandwidth, but overall we will get a lower gain compared to transistor B. Now be careful, as we have seen, at lower frequencies, gain is no longer limited by gate resistance, gain is limited by stability. The gate drain capacitance plays a much larger role at lower frequencies. And that brings us to question 2C, the third question of the second homework. So what are the two major limits? There we go. What are the two major limits to achieve high gain at millimeter wave frequencies? How can we optimize this in layout? The two major limits are indeed gate resistance on one hand, especially close to the fmax. You can minimize it by clever layout. We have seen a few examples. The second important limit is stability. Unstable behavior from CGD. CGD can also be minimized by clever layout, but a much more common approach, a much easier approach would be this neutralization, where you make use of a differential amplifier and then you have the cross coupling with a neutralization capacitance to neutralize the effect of CGD. How do you know what's now the best finger width? If you have a transistor with a total width of 100 micrometer, how would you do that? What we typically do is in a new technology is you start with a finger width of 1 micrometer. This might seem like an arbitrary choice, but very often in many planar and also FinFET technologies, we see that, no, I should say fit planar, we see that the finger width of 1 micrometer. In FinFETs, obviously, it's different. In FinFETs, we typically try to minimize the number of fins per finger, but the 1 micrometer finger width very often is already a good starting point. And start with a small transistor. Do all the entire parasitic extraction of all the interconnects, maybe up to metal 3, 4, 5, and see what you get in terms of gain at a certain frequency and also in terms of fmax. And then you would decrease the finger width or increase the finger width and see if this really impacts fmax, but also keep an eye on your input and output impedances. Right? And that typically that approach would give you an idea of what is a reasonable number of good finger width for my transistor size. Typically, the larger the transistor, you would kind of be tempted to go for larger finger widths because that would reduce the number of fingers that you need to put in parallel. Let's move on to question D, fourth question of homework 2. There was that schematic with very simple pseudo differential pair. It's not a real differential pair because there was no current source at the sources, so we call it a pseudo differential pair. You can simulate that in CUX if you want. The question is how can we increase the gain of the amplifier? That's typically done by capacitive neutralization. If you are in the region where the transistor is potentially unstable, you really want to neutralize it. Neutralizing is easy. Unilateralizing requires a bit more effort. It would mean that we add, in series with the neutralization capacitor, we add a bit of resistance to really unilateralize that transistor. But neutralization is it's easy to implement. Ideal capacitor between input and output. For this example, we had to add 9 femtofarad also to minimize the S12. S12 is not 0. We did not unilateralize it. If it would be unilateral, S12 would be equal to 0 or minus infinity in dB. But it is fairly small, such that you can design your input and output matching networks fairly independent from each other. The drawback of neutralization is always stability in common mode. And that can be compensated by looking at your common mode path, which is typically the bias path, and adding losses in the common mode. and making sure that those losses are only seen in common mode and not in differential mode. So that's typically done by adding series resistance in the gate bias lines. And then the last question or sub question, how can we make the input impedance easier to match to 100 ohm? Maybe I need one more slide here. So if you have a transistor, easy approach is of course to put a resistor here, a resistor in parallel or a resistor in series, a physical resistors. Terrible for noise figure, terrible for GMX, so definitely not the best approach. But what we start to see also at these high frequencies is that we do some form of what we call inductive degeneration. You put an inductor at the source and that reduces the gain, yes, but it also makes it more linear, it also makes it more stable, and definitely the input resistance, the AC input resistance is much closer to 50 ohm or to some reasonable number, reasonably close to the output impedance of the previous stage. So the technique on the left is typically what's done in microwave, just add losses to make sure everything becomes stable, but there is a huge penalty to pay on the gain. Whereas the technique on the right with source degeneration, if you have sufficient margin, if you have sufficient gain with respect to the fmax, or if you're sufficiently far away from the fmax, then the technique on the right, the inductive degeneration, is definitely something that you can use. And then the final question, if you do that complex conjugate matching, most of the time you end up with a stability problem. And that's simply because complex conjugate matching, in theory, if you can do it losslessly, or if you can do it without any loss, it will give you the highest gain. And if the transistor can oscillate, well, then the highest gain is infinitely large. So if the transistor can oscillate, then it will oscillate with complex conjugate matching. Right? So that's the reason trying to get high gain, you try to do complex conjugate matching and you will end up with a stability problem. How is that solved? You can solve it as we have seen. Adding losses makes it also easier to match. Better approach is to add neutralization, but then you have to be careful about the common mode behavior. But also this source degeneration might actually be something to look at, maybe in combination with the neutralization, to really come to an amplifier stage which is easy to match at the input and output, but also gives you good stability and also gives you sufficiently high gain. So I hope that with these questions you were able to better understand the concepts that we have seen in lecture 2.